Hi, my name's Joanna Nicholas, and I'm a welding engineer for a company called TWI Ltd. I'm a STEM ambassador and kind of wanted to illustrate how AI can be used and has been used for quite some time in manufacturing and the welding world. The main topic that I'm going to be speaking about is about weld zone hardness, and I'm going to start off with a bit about why we care about it in the first place. Why do we want to know about hardness? The hardness of steel particularly is an indication of the strength of the material and the microstructure of the material. And those are really important because the strength of the material and the microstructure, the crystal structure of the atoms in the steel, can give us some clues about whether we're going to face problems during the fabrication stage or the service use of the material. There are some standards that exist that have restrictions, and if we can predict what the hardness values are going to be, then when we're coming to make something, it's a bit easier to make something if we know where we're headed to, what things can be changed, and pre-selection of how we're going to make it. So these critical hardnesses for cracking relate to two main aspects: the fabrication hydrogen, that's hydrogen cracking that happens because of making stuff, and then the hydrogen cracking that can happen during the service, so during use. And you'll notice that fabrication hydrogen cracking has got much higher hardnesses listed than for service. We can accommodate something more during fabrication than we can do during service, and that's to do with the environment in which it's being used. This severe hydrogen sulfide containing environments have greater restrictions because of the way that the hydrogen generated from the acid hydrogen sulfide reaction behaves subsequently. But effectively, that hydrogen cracking can always be considered to be a combination of three major factors. Those three factors are the microstructure of the material, how much hydrogen we can get into the material, and the stress or the load that we're putting on the material. If we can adapt any one of those things, we can avoid the problem. So avoiding the stress, well, we're going to want to apply stresses. So we're going to want to apply loads to the component during service. So that's not really something we can do much about. The hydrogen, well, we can modify it a bit, but it's generally there. The thing that we can really do, particularly in welding, is modify the microstructure. If we modify the microstructure, then we can usually make it small enough so that it doesn't interact with the hydrogen or stress anymore, and the risk of cracking is gone. So by modifying the microstructure, that modifies the hardness, and that results in a better outcome. Just as a quick teach-in on fabrication hydrogen cracking, and then a little bit on service cracking as well. Fabrication hydrogen cracking can occur at various different places in a weld. Could be along what we call the toes, or underneath the beads, from the root of the weld, or across the weld. And what happens is that hydrogen gets into the weld pool when it's molten and then ends up in the solid material later. The hydrogen is dissolved. It's atomic hydrogen rather than the diatomic hydrogen that we would normally expect. It's not H2, it's just H. And if we get enough of it in, then it can lead to cracking if we've got enough stress. Different locations where it can appear, and it appears a bit like this, pictures too, and it can be called lots of different names. Fabrication hydrogen cracking is the one that I would choose, but it could be called delayed cracking, cold cracking, because it happens when the material's fairly cold, down to about 150 degrees C. And it can happen in different locations, maybe in the HAZ, that's adjacent to the weld, the heat affected zone. So that's the parent steel that's not been melted, but it's been changed a bit because of the heat of welding, or in the weld metal itself. And then another couple of pictures of where it can happen. Again, the weld toes, those are those corners where the weld metal meets the original parent steel, or in the root, that's in the bottom corner, or under bead cracking. And we've got this kind of abbreviation CE. CE is a compositional parameter called carbon equivalent, and I will be talking about that a little bit more later. So if the carbon equivalent, if the parent material is higher than that of the weld metal, we tend to get cracking in the heat affected zone. If the carbon equivalent is less in the parent material than in the weld metal, then the cracking tends to be in the weld metal. So those are all those locations that's going on in this fabrication hydrogen cracking. I also said that service hydrogen cracking has got a much lower hardness limit, down to 250 Vickers hardness. And that can occur anywhere in the weld zone. usually associated with the heat affected zone, but it might not just be like immediately close to the weld. It might go on into the parent material. It's usually a bit branched and looks like a tree because of the way that the cracking happens. So obviously we don't want any cracking in something that we've made. So we do want to try and avoid it by modifying the microstructure. The microstructures are always based on what is the composition of the steel and then what's the thermal history. The thermal history comes from the welding process itself, from the solidification of maybe the parent material. What processing has it had? Have there been any heat treatments? Has there been any welding? Because welding is another solidification or heat treatment of the material. And then for steels, there's any heat treatment that takes the temperature up above about 720 degrees C, changes the structure, the microstructure. The microstructure is just how the crystals are arranged, and that can be changed as long as it's been hotter than 700 degrees C. And then we've got something called post-weld heat treatment, and that also affects the microstructure that we end up with, and so the hardness. To get what the hardness is, we need to know something about the composition and something about the thermal history. So this carbon equivalent that I mentioned before, it's a shortcut to sort of rank steels in line with their weldability, how easy it is to weld them, based on the hardness of the heat affected zone. There are two main ones, the IIW carbon equivalent, which is given at the top there, and the PCM, which is given at the bottom. In general, they all start with carbon, and then there are other elements that are included in these carbon equivalents which give us a clue as to how hardenable something is. The key thing to note for these is that if the carbon is lower, the other elements matter a bit less. We would generally switch from the IIW carbon equivalent to the PCM if we're looking at lower carbon content steels. But those aren't the only carbon equivalents out there. There are lots. So here's 5 different carbon equivalents. The IIW carbon equivalent at the top there with the addition of a silicon term. Then we've got complicated CEN, and then we've got some other carbon equivalents that are used. All of them are doing the same sort of job. They're a shortcut for composition. We're trying to define what the composition is, and we're going to use a carbon equivalent to try and work out what that is. Now, in the 1960s, there was quite a lot of work done at TWI, which managed to say there's a relationship between carbon equivalent and hardness, and we can make use of that to help estimate whether we're going to get a problem with fabrication hydrogen cracking or not. And so this diagram is taken from a European standard, which tells us how to weld successfully without getting cracking based on that work from the 1960s. You can see we've got lots of nice straight lines and a prediction table that says if I've got a particular combined thickness and a particular heat input, and I know how much carbon equivalent I've got and how much hydrogen's there, I can predict what preheat I need. The standard includes about 20 of these images for different combinations of hydrogen and carbon equivalent. The reality is a little bit different. The carbon equivalent does change with carbon equivalent leads to a particular hardness with changing thermal history parameter. And so, for a higher carbon equivalent, we can expect a higher hardness for the same thermal history. And we kind of end up with that as our basis of what's going on. So when we're thinking about welding, we think about a single pass weld. That's just one weld bead deposit. It's a rapid thermal cycle, and it can be described quite easily by the cooling rate, a particular temperature, usually cooling rate at 1000 degrees C or 700 degrees C, or a cooling time parameter. Convention currently is that we use the cooling time from 800 degrees C to 500 degrees C as a definition of what the thermal history has been. But after we completed our welding, we might do some post-weld heat treatment, PWHT, which is a slow thermal cycle. Everything's heated up very slowly, held at a particular temperature for an amount of time based on how thick the material is, and then allowed to cool down. Those different elements, the heating rate, the hold time, the hold temperature, the cooling rates, can be separated out or can be combined into a single tempering parameter, something called the Holloman-Jaffe parameter, is often used. And when we're thinking about multi-pass welding, where we're putting down more than one weld bead to fill up a joint, then we're using a combination of those two methods to describe the thermal history that we've experienced. So this cooling time from 800 to 500, it depends on the thickness of the weld material that we're going to be putting down, how much heat is going into the material. That's called the heat input. The joint geometry, so if we've got a butt weld where the two plates are put next to each other and we're just joining them together, or if we've got a fillet weld, which is like a corner joint or a T-joint, then that will be a different geometry and result in a different cooling time, even if everything else is the same. And the preheat, how much heating we do of the joint before we start welding. All of those things contribute to changing the 800 to 500 cooling time. Now, in concept, cooling time and hardness are related to each other like this, where at low cooling times, we've got a particular microstructure called 100% martensite, which gives me a hard microstructure, the maximum hardness. And then at large cooling times, we end up with no martensite, so a lower hardness. And in between, there's a transition between the two, where we're moving from that 100% martensite down to 0% martensite. So that concept is where everything else is relates to, because we want to have the target hardness, and we might be in the 0% martensite, we might be at 100% martensite, we might be in the transition region. That cooling time, carbon equivalent and hardness, can be related by looking at different rates. So we've got that cooling time and some hardness on the graph, with increasing carbon equivalent as we go upwards. So you can see that as we increase the carbon equivalent, the value of the predicted hardness goes up for the same cooling time. So if I want a particular hardness, I need to choose a lower carbon equivalent or a longer cooling time, depending on the actual conditions I've got. So think about applications then. For applications, we start with composition which is known, or it's within known limits. Steels come to particular grades or particular standards, and those allow us to choose a known composition. The cooling time that we get depends on the welding parameters, the preheat and joint configuration, and can be calculated. There are standard methods for that, or there's some very complicated maths and modelling that can be done that can predict what the cooling time is going to be. As a result, we can then say, well, what's the maximum hardness going to be? If we know the composition and we can work out what the cooling time could be, what's the hardness going to be? The methods we would use would be either an empirical model or a neural network. So then that brings me back to AI. Why does that fit in, and how does it fit in? Well, it's a multifactorial problem. You see, we've got the composition and we've got the thermal cycle, and the thermal cycle itself is a multifactorial problem as well. We've nearly always got a limited data set, and so AI is not new, but it's got its roots in neural networks, and there are some limitations still. For this particular problem, the AI model, or the neural network model that we've got for it, is based on a limited data set. That then means that because we've got a limited data set, we've got to put some boundaries around where we're confident that the model can work, or the AI will work, and how far outside of that data set the AI can still be considered to be relevant. So how did we do it? Started off with a literature review, looking at lots and different places where the thermal cycle or weld data was reported alongside the hardness data. And there have been a number of attempts to model the combined effects of composition and welding parameters. And there were lots of different models that existed. Every model gave a good fit to the own data set, but not necessarily to others. They did have that same approach where we had low 800 to 500 cooling time, so it's 100% martensite, a high 800 to 500 0% martensite region, and the region between the two. And the data that we got said that some of the models didn't really work very well. So you could do that visually just by saying, well, okay, if I've got a one-to-one line, how do they look? And we've looked at the individual models and combination of models and a neural network. Here's my data using one of the models that was in the published literature, our predicted hardness to the model against the measured hardness. And most of those dots show that the measured hardness was higher than what was predicted. Most of the dots are underneath the line, which suggests that the model is generally unconservative. This one from 1981, also the line was just the wrong side. It wasn't everything in the middle, It was biased towards left, which then meant that the model was over predicting the hardness. So these empirical models that had been generated by these researchers some time ago didn't quite work. So taking that unconservative and conservative model and combining the two, we actually get a much more even distribution. And this then showed that you could use this empirical model for these about 300 data points. And it worked for those data points reasonably well, with some caveats that about 50% of the items the model predicted a lower hardness than it would be, and for 50% it would be a higher hardness than it should be. But the spread was quite good. Standard deviation was 25 hardness points, so 2 standard deviations, 50 hardness points. So it was a usable model as an empirical approach. So using that same 300 data points, using a multi-layered perceptron type neural network, those 300 data was split into 100 data for training, 100 data for testing, and 100 data for validation. When we're looking at it, we're trying to say, well, I've put these information into effectively an AI. I've trained it on the first set, tested it with the second set, and tried to validate it with the third one to say, does it really work? That's something that's often missing in our understanding of AI kind of more globally now. We know that we've trained the AI model, things like ChatGPT on the internet, but the veracity, how true the information is that's gone into the AI is unverified. We haven't checked what the AI has been trained on because it's been trained on such a large database, and it doesn't know what's true and what's not. There hasn't been that rigor in that model. There's a limit sometimes of how much we can use it for. The neural network results were similar to that for the empirical model. We had pretty good one-to-one correlation. Again, standard deviation of around 25. This one was slightly less, 24 rather than 25, but standard deviation of around 25. And the neural network model could be used, but we had to put some boundaries around it, because just like for the empirical model, I would say don't use it outside of the test data. For the neural network, using it outside of the test data was possible, but we had to put some boundaries on it. Said, well, how far can we push the composition, the different elements in the composition? The carbon equivalents, how wide could we be? So we allowed plus or minus 0.1 carbon equivalent at the extreme ends of what was allowed, because then we could be confident that we weren't straying too far out of what had been trained on. It's important to kind of make that caveat, because we don't know whether the model would have that same relationship between hardness, composition, and thermal cycle for a different composition, because as we change the composition, the way that the thermal cycle affects the material changes. So if we go too far, for example, if we used a high chromium steel rather than a low chromium steel, would that make a difference? Yes, it would, because the higher the chromium, the more the way that the heat interacts with the material changes. So we do need to put those caveats around the neural network. So we can't just use it for every steel that exists. We have to say, well, it's okay up to 3% chromium because it's been tested on up to 2%, and we're happy that we could go up to 3% without falling outside of that. But I wouldn't be comfortable using it on a 5% chromium or 9% chromium steel, for example, because the way that the material reacts is different, and the neural network doesn't know that. The AI doesn't know that there's a difference in the way that the material behaves as chromium increases, because I haven't told it that. I haven't trained it in that way. So I do need to just put some boundaries on the way that we use AI. Both the models result in this sort of approach, whereby we've got this high hardness, low cooling time model, which then transitions not as a straight line as the concept, but in a sort of curve. And then we actually don't end up with it. We end up with some kind of continual softening with very large cooling times, which is more accurate to what happens in real life. So for applications to real life, works beautifully for a single pass weld, but that's not very practical for most welded joints. What happens in the heat affected zone in a multi-pass weld? Can we model it? And how does it help the welding engineer? Well, we can consider the weld thermal cycle as a series of heat treatments, and we can kind of separate out the heating and cooling curve as kind of little segments that are then added together. And we use this Holloman-Jaffe time temperature parameter, which I spoke about when we talked about post-weld heat treatment earlier. The Holloman-Jaffe parameter gives me a value of H, which is the temperature multiplied by a constant plus the logarithm of the time, all divided by 1,000. And the hardness is the as welded hardness minus a change in hardness. And that change in hardness, delta HV, depends on the composition and the Holloman-Jaffe parameter. So that works for post-weld heat treatment, but it can also work for the weld thermal cycle. If I separate my weld thermal cycle, which is a temperature and time representation, looks like the red line, I can sort of decide that actually, instead of just considering a continuous value, I could consider it as steps. And if I consider smaller steps, that's better than the large steps that I've shown in this schematic representation. But you can see that the same form is there for the stepped version as for the continuous real life version. So a second thermal cycle can be considered to be a lot of little post-weld heat treatments. So each of those steps represents a post-weld heat treatment, and then I can use that same approach that says the hardness is the original hardness minus a change in hardness, and that change in hardness depends on the composition, the initial thermal cycle, and the Holloman-Jaffe parameter H of the second thermal cycle, and if we've got post-weld heat treatment, that as well. Well, how does that all help a welding engineer? Well, we're back to that hardness prediction to try and get to a particular welding procedure. The absolute prediction is not actually accurate enough, plus or minus 25, both for the neural network and for the empirical model. Is not accurate enough to be useful on its own, but we can predict what's going to happen if we change something. So we can say, oh, actually, because I've got this second weld pass, that means that the hardness is actually going to go up. If I choose a different welding parameters or a different preheat, I can change it so that the hardness comes down. And is it below the level that I need, those critical hardnesses for cracking? And that can save quite a lot of effort. Rather than just doing a weld it and see approach, we can do the prediction and help get it right first time, or having a particular procedure that we already use, but we want to use it on a different composition material. How does that affect it, and can we modify it more easily to do that? Well, I hope that's been okay for you. Thanks for listening.